Several times so far, we've seen we've had to use type classes to allow us to do things where we don't know what the type is specifically, but we do know that we want some features of that type. So here's a kind of example we've seen quite a few times so far. If we want to search through a list of key value pairs, and we've got a key k, then we're going to have to ask ourselves occasionally whether or not two keys are equal. So if we've got searching for the key k and we've got a key k prime, we're going to have to say, is k equal to k prime? Then if it is, then we return that value. Otherwise, we carry on searching. Now, in order to actually be able to do this comparison, Haskell needs to know that the type k here, which could be any type, does support an equivalence checking function. So we can actually get this equals equals sign to work. If we take away this part here, where we're telling Haskell that k must be an EQ type, then it will reject our definition. So it'll say no instance for EQK arising from a use of equals equals. So to use equals equals, we have to tell Haskell, or we have to have it in our type signature, that k is a sort of type that has equality. So one may wonder, well, what types don't have equality? So let's have an example. So let's say we're searching for the identity function, so that's this, in a list where we store the keys are functions and we store them with their names. So the identity function is the identity and the not function we call not. And so now this isn't going to work because it says there's no instance for EQ bool arrow bool. So these functions are all of type bool arrow bool. So there's one that just takes a boolean to a boolean, and this one takes a boolean to its inverse. And now it's complaining that this type, bool arrow bool, doesn't have an EQ implementation for it. So previously we've used search for things like strings and integers, but we now can't use it with functions because there's no way of comparing functions for equality. And in general, this is because a function may take infinitely many possible different inputs, and we can't possibly check for all possible inputs whether two functions give the same answer, which is what we require for an equality test. So this type class thing prevents us from calling functions with types that can't actually do what the function is asking for them. So if we call it with k being a function type, then we won't be able to compare them for equality, and it won't know what to do. So this stops us at the type level from calling such a function. But let's look at this EQ type class in more detail now. So what is a type class? A type class is a collection of types which all have some common functions. And we can find out what these common functions are in GHCI by typing info and then the name of the type class, in this case EQ. So it prints out quite a bit of stuff, and most of it is telling us what types do support EQ. But if we go all the way up to the top, then we'll see what the class definition is. It says there's a class called EQ of some type A, so this could be integers or strings or something. And then it must have two functions. There's an equality test, which takes two A's and gives us a bool, and there's a disequality test, which takes two A's and gives us a bool. And then this comment here is saying that the minimal definition is we have to give one of them. If we only give one of them, then Haskell will know to define the other one as not the other one. And then down here, we've got a list of all the types which already have equality definitions for them. So strings actually falls under this one. They say that if there is an equality implementation for some type, then there is equality implementation for lists of that type. And this one here says if there is an equality implementation for integers, floats, doubles, chars, bools. And all these ones down here are for different sizes of these tuple types of many different components. So why is this useful? So I've already said it prevents us from calling functions like search with where we're trying to search for keys which are functions, which just wouldn't work. The other way it's useful is we can define our own instances. So far we've done things like data with some data type, let's say direction, it's just up or down, and then what I wrote was deriving EQ and show. And what this does is it generates a function which is essentially this. It generates the equality function on directions. And then, as we saw in week 1, up and up are equal, so return true, down and down are equal, so return true, and anything else is false. And you can see this saves us quite a bit of typing, because in general there could be many constructors, and the constructors could have arguments, and we have to work out how to test those for equality as well. Now we can't write it like this, and try to write it, then it will say ambiguous occurrence. It doesn't know whether it's the equals from the EQ type class or this equals here. But what we can do is give our own instance for EQ direction. And then we can't actually put the type definition there. And then this still won't allow us to do it, so let's just see what the error is. Because there's now two definitions. We've got one from the deriving here, and one we've defined by ourselves. But if we take this one away, then we have our own custom implementation of equals for directions. And now we can change this however we want. So we could in fact say something like all directions are equal. So whatever we give it, it will say 2 directions are equal. And now we get into a case where we can say up equals down, and down equals up. So this doesn't seem particularly useful just for this small example. In fact, I'll set it back to how it was before. Oops. But there are examples where it is useful. So let's think about how we might make a type of case-insensitive strings for comparing strings excuse me, up to their case. So let's call it case-insensitive strings, CIS. And it's going to be a new data type with this one constructor, mux.cis, and this is the string stored underneath. Now the important thing is what we want to do is store strings as they are, but when we compare them for equality, we're going to only compare them up to their case. So how are we going to do this? So we're going to do an instance declaration. We're going to define what equality means for case-insensitive strings. And now we're going to define the equality function. I'm going to say string 1 is equal to string 2. So now we have to unwrap, we have to pattern match on the constructors. I'm going to say these two strings are equal if, when we convert both of them to uppercase, they're equal. So I can do map to upper string 1 is equal to map to upper string 2. And now we can make some strings that are case insensitive. So we might make 1 is a case insensitive string, and 1 is just CIS 1. And now if we ask if 1 is equal to mux.cis 1 in capitals, we'll get back true. But obviously if we compared these just as normal strings, then they wouldn't have been. And it doesn't actually matter where the capitals are, it always compares them as equal. Another example of a type class is the show type class. So you can see this, so I've done deriving show here. And what this does by default is generates a type class that just prints it out in Haskell notation. But this may not be always what we want when we just want to look at the values. So for example, here's a type of compass directions, and I've given it deriving show. And so this just gives us back north as north. But if we're printing out lots of directions, for instance, you may just want to give them short names. So we can do this by giving a custom show instance for this type. We would say instance show for compass direction. Where? Now what do we write here? We have to give it the right function to show things. And we haven't really seen that explicitly so far. So let's type info show to see what's going on. And now it will show us all the different types which support showing, all the way back up to the definition. And it shows us that there's actually 3 functions which are part of the show type class. So any type which implements show implements these 3 functions. And the minimal one we need is either shows with precedence, this one which takes an integer argument, and we'll just ignore that for now, and a show itself. So show just takes something of the type that we're saying is showable and gives us back a string. So we need to implement show, and then we need to say what it does for each of our constructors. So let's just say it's going to give us the single letter, the initial letter for each of the directions. East and west. Oops. So if we reload this, now when we type in north, rather than giving us back the whole thing, it will just give us n, using our custom show notation. So in summaries, type classes are a way of categorizing types into their capabilities. So we've seen that some types are EQable and showable, and later on we'll see many more different kinds of interfaces for types. So one could think of this a bit like interfaces in Java, except a little bit more general. And we can often get the compiler to write an EQ or show instance for us by doing deriving. But writing our own instances is sometimes useful. So we saw that with the case-insensitive strings and with a show instance for compass directions.